In our last video, we wrote a scratchpad assembly program that was designed to print out Fibonacci numbers up to a certain point. You can see here that that point was 317,811. We did purposefully include a small logic error so that we could kind of troubleshoot it when we debug it in this video and get that all fixed up. And just to remind you what that looked like, we're going to just recompile this here real quickly. And then we'll go ahead and run it. And so we can see that when we call the executable, we print out Fibonacci numbers all the way up until 514,229, which is one step further than what we expected. So the first thing we want to do is go ahead and open our program. So we're going to go to File, Open, Fibonacci loop.exe. So the first thing we want to do is go ahead and open our program. So we're going to go to File, Open, Fibonacci loop.exe. Okay, so first let's set our breakpoint. So we're going to go to Symbols. We're going to go to Fibonacci loop.exe. Whoops. And we're going to search for our first label that we're really looking for, where all of our core logic happens, and that's next fib number. So here we go. And we'll just go ahead and jump there. And now we can see the next fib number jump right here. So we'll go ahead and set our breakpoint at the first thing after the jump. So essentially what happens is every time we call the next fib number, we're executing this sequence of instructions. So this is going to allow us to examine the registers in the memory each time that function is called and see where we made our mistake. So let's go ahead and run the program. And we can see that we've hit our breakpoint right after the jump to the next fib number. Now this is our RIP register. Our RIP register points to the next instruction to be executed. Let's take a moment now and compare the assembly code to the disassembled code. So we can see here that we have our first int, second int, max int. We already interacted with the title string, and our jump to our label next fib number. So here we have our max int, second int, first int, and our fib number. The only thing that we would have in registers right now is our max int in R14D, which is the lower 32-bit. So if we look at R14, we can see that we have 4D973 in R14, which is what we are comparing to for checking the maximum number, which is of course where our issue is, right? So let's do a mental run through of what is supposed to happen, right? So what's the first thing we're going to do? We're going to move whatever is in first int, which is 1, into EDX. We're then going to move whatever is in the second int variable right here, which is 1, into ECX. And you can see that's exactly what we told it to do. Then we're moving RDX into R15. RDX into R15. And then we're going to move EDX into the first int. Now EDX and RDX are portions of the same register, right? So RDX is the full 64 bits. EDX is the lower 32 bits. And then we are moving so D on some of these larger numerical registers, which we will go over in another video, is the lower 32 bits. So R15 is 64, R15D is the lower 32 bits. So we're moving these 32 bits into the first int in RAM right here. This first int variable will be held in RAM. And then the R15D, the lower 32 bits of that, into the second int variable in RAM. The next thing that's going to happen is we're going to load the effective address of the fibprint string right here. We're going to load the address of this into the RCX register. Now keep in mind our Windows application binary interface. It states, and you can look this up in Microsoft documentation, the argument should be passed into RCX, the second argument should be passed into RDX, the third argument should be passed into R8, the fourth argument should be passed into R9, and then the rest of them go on to the stack for integers or some of those kinds of arguments. For floating points, we would use like XMM0, XMM1, XMM2, XMM3, and so on and so forth. And we can get into those specific ones later, but for these general purpose functions, we were going to go into RCX, RDX, R8, and R9. And remember, those are somewhat analogous. The lower 32 bits can be interacted with ECX, EDX, R8D, and R9D. So once we load the effective address of fibprint into RCX, which is going to be our first argument, remember our ABI, we're going to call a function. And so this is going to be the argument to that function printf, the next number %d. Then we're going to compare what's in R14 and what's in R15. That's going to set a flag. We're going to jump if less than to the next fib number loop, or label. And we're going to jump if greater than to the end routine. So this is essentially an if statement, right? If it is less than its maximum number, we're going to jump to the top of the loop again and go through it, increment it through the next fib sequence. If it is greater than or equal to its maximum number, we're going to jump to the end routine, which will return calling power or the essentially instruction pointer to this main C program that we took from Randall Hyde. And our ASM main function, this will return, and the next things in the C program will start to be executed. So if we go through this mentally first, right, we'll put 1 into EDX or RDX on here. So 1 will be in here, which it already is. 1 will also be moved into ECX, so the lower 32 bits of RCX will have 1. Then we're going to move what was in RDX into R15. Then we're going to add what's in RCX and RDX, so these two numbers will be added, and the result will be put into RDX. Okay, so let's go ahead and execute this. Okay, so now, right, RDX has 1. The next thing to be executed will be moving 1 into RCX, right? Then we're going to move RDX into R15, so we can see R15 right now is all zeroed out. If we execute the next step, it will now contain 1. Then we're going to add RCX and RDX together. So RCX is 1, RDX is 1. We're going to add them together. We're going to get 2 in RDX. Right? Now we have 2. Now we're going to move EDX into the first int's location in RAM. And then we're going to move the lower 32 bits into second int, which is another location in RAM. Now we're loading the effective address of the fibprint string into RCX so that when we call print, it's the first argument. Now we are going to call that printf statement. So let me pull that window up. Oh, wrong window. And when we execute the next step, we have now called print with our number as the argument. Now we need to compare R14 and R15, right? We need to see if we are, where we're jumping. We are jumping, we just don't know if we're jumping to the next fib number or to the end routine. So R14 and R15, let's take a look. R14 is much larger than R15, right? So we are going to execute the next step, and it's going to jump to the next fib number. That's going to bring us right back here. We're going to execute this again. You can also see the flags that will be set here. Okay, so we jumped back, and now we will essentially repeat that same process again, right? So we have our first number, we're moving first int from RAM into EDX, so RDX. So let's go ahead and execute that. Then we are moving our second int variable into ECX, so RCX right here. Then we are moving RDX into R15. RDX is 2 into R15. We're adding RCX and RDX and placing the result in RDX. And then we are moving what our end result was, so 3, back into that RAM address. And we are moving the R15D, so the lower 32 bits of this, into the RAM address for the second integer. Something interesting that you will see down here is this. We can see if we go into our memory map, our data portion of our program starts at 7FF6166D5000. Obviously that's a hexadecimal address, that's not, base 10. And then the next exception information portion starts later, right? That's the boundary. So if we look back here, we can actually see the RAM addresses for these right here, right? So if we step through this program a little bit more, remember we're going to jump to the next fib number because we're comparing R14 to R15. R15 is lower than R14 by a great deal, so we're going to jump back. Okay, so now let's keep an eye on not only the registers, not only the instructions, but also the RAM addresses, right? So moving the result or the number contained in the first integer RAM address into EDX. So RDX is 1. And that first RAM address, where's my mouse? There it is, 3, we're moving into this register. Right? Okay, there we go. So we have 3, which came from here. It was copied from here to here, right? The next thing that we're doing is moving the value stored at this RAM address, second int, into ECX. So ECX will now contain the next address, right? The next value. So RCX, the full 64-bit, now contains 2, right? So now, again, we're going to move RDX into R15, RDX into R15, and then add RCX and RDX and place the result in RDX, so 5. So as we keep going through this, we will continue to increment these numbers. And you will notice, right, that says D, these are in hex, right? So these are not in base 10. And we can also see that we are at the same time printing out those results, right? This is stepping through how the program would actually execute on the CPU. So we're just going to very quickly step through most of these. we are primarily keeping an eye, if any of you noticed, this is the hex representation that we are comparing to, right? So R14 has the value 4D973, and here we have 4D973. Of course, because of the endianness, this looks transposed, but it's not. So as we continue to go through, we will get closer and closer and closer to that max value, right? And we can also, again, confirm that out here. So we'll step through one more time. Now you can see we are already at the value that we should have. This should be the last loop, right? We should have compared and said, okay, we are now greater than or equal to, right? The jump to end routine if we are greater than or equal to R14 to R15. The issue being R15 does not contain the most updated output. It is one step back. So if we go again, right, this is in the 04D973. If you remember, this is our first int RAM address. That's already contained here. We should not be adding this, our absolute max boundary, to anything else and printing out another number, right? So we'll step through this. And you can see after add, we get a value, right? So we're adding what should be right here, what should be our maximum, to something that's greater than 0. So that's bad. And we will now jump okay, and now add those, call it, and now we have printed a number that is greater than the boundary we expected, right? So we can see that now that we have already done the addition, right? We did the add RDX and RCX. We are one step back with R15. Only now does R15 contain the value that we are comparing, the updated value that we are comparing against for the 317,811. So now when we compare, we're going to jump to the end routine because we're going to be greater than or equal to, right, these two numbers on this compare R15, R14. R14 and R15 are identical. So because it's equal to, we're going to jump to the end routine. So if I hit F8 a couple more times, we're going to step through to the end, or I'll just run it to completion. And that's done. Okay, so let's address the logic error here. When I first wrote this program, fib number was going to contain the current Fibonacci number that we were on. We were going to compare against that. We are not doing that now, so let's go ahead and get rid of it. It is an unused variable. Always bad practice to have. Okay, so from the logic standpoint, we are moving, in terms of what we're comparing with R15, we are moving RDX into R15 before we add. So that means that R15 is only updated after each cycle, right? R15 is updated here. So the first int is moved into EDX, the second int is moved into ECX, RDX is moved into R15, so the first int is moved into R15 here essentially. We don't update that after. So once we do the addition, there's nothing that's moved back. So something we could do is to place what we put into the first int here after the addition into the register we're comparing. So if we move into our 15D, our first int, we will then add RDX and RCX, move the results into first int, And then down here, before we compare, we're going to move the first int into R15D for the comparison. So let's build that. Oops, the debugger has it open. Let's build this and then go ahead and run it. Oh, it wasn't saved when we built it. Okay, let's save it and then build it. We now get the correct output, and if we want to just double check that in the assembly, we can file, open, fibloop. We have our breakpoint set, so we'll go ahead and run through this. We can see R15 for the comparison. So now we're at 196,418. And if we follow the memory map for our data, we can see that here as well. And now that we've done our addition, we can see that our first int actually contains the right number. And if we, it's over here, we will call the print out the right number. So then we're going to move the thing we added, right? We're going to move first int, which, remember, this is the RAM address for that, into R15D. We can see right here, move first int into R15D. So we'll execute that. And now we see that those have the exact same number, our boundary in R14 and our working number in R15. And then we will compare R14 R15, of course, because these are identical numbers. This will not jump if less than, because it's not less than. It will jump if greater than or equal to the end routine. So we'll pass that. And then jump to the end routine. And then we can let this run its course.